Nobody can hear me? Okay, now it works. We've got 1 more minute, but Jeff, maybe if you want to start sharing your screen.
Okay, let's see if we can make it work 2 times. Full screen.
Yes, good, that works. And I believe you will automatically get time warnings from someone, not me. So
Okay.
I'll just be available at the end.
All right. And you can see my cursor?
Yes, you can see it also.
Okay, great.
Good, well, thank you, Jeff. Take it away.
Okay, great. Thanks for the invitation to speak at this meeting. And good morning to all of you. I wish I were there, but unfortunately couldn't be there this week. I've worked in the area of FRBs for more than a decade. But in recent years, I have actually not spent very much time working on FRBs because of my role as a project scientist for the Event Horizon Telescope. With the new initiatives within ASIA, I've gotten re-excited about what can be done with FRBs. So actually preparing for this talk has been quite informative and useful for me to think through what the possibilities are and what we know about, understand what we currently know. So I'm going to focus on the realfast system, so real-time commensal fast transient surveys with a very large array. I'm going to take a little bit of a historical perspective as to how we got to building this system to try to get some sense of the lessons learned and the motivation for carrying out this experiment, and then talk about what we have learned, what the power of the realfast system is, and what the future opportunities are with it. So I want to emphasize that realfast system was put together by a relatively small team, and you see 2 of the really key people here on the left, Casey Law and Sarah Burks-Ballauer, who did a lot of that work. You can see some of the rest of us creating some RFI in the plains of San Augustine, where the very large array is located. For me, the road to the realfast system really began with the fly's eye experiment with the Allen telescope array, and so this was a search for FRBs that we launched shortly after the first Lorimer paper was announced. And you can see from this peculiar photo, so the Allen telescope array is an interferometer, but we used it in incoherent detection mode, so the fly's eye mode, of pointing all the antennas in different directions to get as large of sky coverage as we could. We built some custom electronics rather quickly over the course of a few months to do autocorrelations on each of the antenna streams, and then accumulated several hundred hours of observation motivated by the goal of confirming or rejecting the reality of FRBs, because certainly at that point it was really unknown and uncertain whether or not these were real events or some kind of RFI that we weren't yet familiar with. And so Andrew Simeon, who was a graduate student at the time, did a lot of this work, but it was a major effort. Took several years to process all those hundreds of hours of data once we had collected it. We got some of the kind of obvious things that you get out of when you turn on an FRB machine. We detected giant pulses from the crab. We saw some very unusual RFI right at the H1 band. This is almost certainly from a LEO or MEO satellite with this kind of sawtooth pattern. You know, in testing, got multiple independent detections of a single pulsar. And so, you know, as a demonstration of the many different paths we have for the data to go through. So that experiment was very sensitive to, or it was sensitive to very bright FRBs. You can see the kind of flux limit here, you know, cut into the parameter space, but was not ultimately successful in detecting any FRBs. But I think was a step in the direction of thinking about, you know, the overall event rates for these sources, and also establishing a path that we wanted to follow for future explorations. The next experiment that we undertook, again using the Allen Telescope Array, was the so-called pocket correlator. So we wanted to start doing interferometric localization of FRBs, but we couldn't use the full correlator to operate at a time scale of milliseconds that would be sensitive to an individual FRB. So we designed what we call the pocket correlator, which had just 8 inputs and was able to do sub-millisecond integrations. And this was something we put together kind of on the fly and did as a short-term experiment. You can see in the little movie the detection of a crab giant pulse with this system. Obviously, the imaging beam was not very good, very strong side lobes, but nevertheless, you know, successful to some extent, and also was a proving ground for algorithms that we wanted to use for interferometric detection. And so here you can see a kind of characterization of the performance of different algorithms. So beamforming, so phasing up the whole array and producing just a single time series on the pulsar is kind of the benchmark to compare against. That's the blue here. And then you can see that fitting in the visibility domain, these green elements did equally well, or almost as well as beamforming. And then searching in a dirty image did well at the bright end, but didn't do quite as well at the lower flux density end. And then, of course, a part of thinking about this is not just, you know, what is the optimal technique, but also, you know, what is the cost of carrying out any one of these particular searches. And so, you know, don't think about the absolute numbers here, but these were relative estimates of the cost of beamforming, imaging, and modeling in the visibility domain. in terms of the computing time relative to that. And in fact, the very high cost of imaging, in fact, drove us to develop an algorithm based on the bispectrum. So the bispectrum is constructed out of a triangle of 3 antennas, and it is in some sense a way of doing beamforming that over an entire image, but without having to calibrate your visibilities, or actually to construct the image itself. And you can see that it performs well relative to beamforming, which is shown in red here. And in particular, the problem with beamforming is you have to know where the target is located. The downside to the bispectrum method is that it only is very sensitive when you have very, very bright sources. So sources that are above a signal to noise of 1 on a given baseline. And then it does very, very well. So it turns out that while we explored this as a general technique, it's probably a niche that really can only be used for very specific kinds of configurations or arrays. Finally, the other thing we did with the pocket correlator, and we really viewed this as a kind of a flag in the ground on this in this field, was that we did one of the first intentionally extragalactic searches, looking at Andromeda, and again, not making any detections, but setting an upper limit on the number, on the event rate at L-band at this particular flux density threshold. So this leads me to realfast. So the motivation here was to be able to do millisecond imaging, so exploit the large field of view, or the full field of view of a very large array. Be able to process the data in real time, so not have to have a supercomputer behind it. Be able to get a lot of observing time, and so set it up as a system that worked commensally with other VLA observations, and then do automatic classification and alerts of detections. And so when we, in the mid-2010s, when we put this idea together, this was kind of the context that we were envisioning for around this time, or for a few years ago, in terms of the other instruments that would exist. And you see these various VLA bands here. So we designed the system primarily to work with the low frequency bands of the VLA, although in principle it could be used for any over any frequency range. And the real strength, of course, is the quality of the localization. You see that represented in terms of the images on the right side here, showing how getting down to sub-arc second localization allows you to put to identify where in an extragalactic source the FRB is localized. the data rates coming out of the VLA for carrying out this work are really kind of staggering. They're around a terabyte per hour, and so that required significant amount of computing associated with that, and order of petabyte per FRB, given the detection rate that was anticipated. So the timeline said we began working on not the fully commensal system, but the ability to get high time resolution visibilities out of the VLA correlator in the early 2010s, and carried out some dedicated surveys. Then we had a kind of partially commensal system, and then around 2019 had the full realfast system. And then a major goal, which we've achieved, is to have the realfast system running with the VLA survey. That's the Very Large Array Sky Survey, an all-sky survey at S-band, and I'll talk about that a little bit more at the end. The system is now more or less in the hands of NRAO, independent of those of us who invented it and worked on it, and running on most LSC and X-band observations. This is just some of the technical specifications. The main thing I want to point out here is this was the design. One of the biggest challenge that we were not able to overcome was getting below about 5 millisecond time resolution in the system, and that was a result of essentially bottlenecks in the existing correlator that wouldn't allow us to extract the information more rapidly, and that was definitely a challenge to the ability to make blind detections. So I think I've said most of these things, but I'll just note that part of the automated system was building up a tool that allowed us to evaluate candidates, and so this is a typical plot. This is in particular, this is FRB 121102, and you see various pieces of information that allow you to assess the reality of the system. All of these systems generate a lot of false positives, RFI triggers, so forth, and it's important to have a system that's quite flexible for handling those and managing those. A little bit more on the overall implementation. I won't walk you through all of this block diagram, but the main thing I want to point out is that the way this system works is that we essentially split off visibilities from inside of the LiDAR correlator system that is built into the VLA. And so the typical path for data to go through the VLA is that there's the F engine in the LiDAR correlator, and then there's the F index, and then there's the another F stage that happens in the accumulation, and another F stage that happens here. And the flow visibilities go out into the VLA data archive, and we pull these off at a high data rate and put them into our own cluster, where we then do the analysis and send out messages. We developed our own code for for searching the data, and you can see the flow chart here for doing this. I would say that one of the really important steps in all this, beyond the typical interferometric imaging pipeline, is a subtraction of mean visibilities, so that essentially we're continually just imaging a blank sky, except for when there is a bursting source. And of course, there's a insertion of mock sources is really essential for understanding your sensitivity and any other effects that might appear. We also implemented a methodology for distributing events, and we worked with a number of other facilities that did joint observations and would follow up when we generated triggers.
Sorry, 5 minutes left.
Okay, thank you. So let me get to some of the results from realfast. The first result, this is before the commensal campaign, was a 170-hour, 150 terabyte survey. So this was capture all the data, write it to disk, and then process it with a supercomputer at a later point. No detections made in that search. The big transformation for the realfast system was the pointing at the FRB 121102, the first repeater that was identified. You can see the discovery image obtained here, showing the excellent localization with the VLA, and of course, a whole host of science followed from that initial discovery, getting the redshift of the faint host galaxy, the discovery of the persistent radio source, characterization of the polarization properties, characterization both of the spectrum and the variability of the persistent radio source, and really, established the extragalactic nature of fast radio bursts and the power of this kind of technique for studying FRBs. Of course, my favorite aspect of all of this was that our work got quoted in The Onion, and I'll let you enjoy these comments briefly. Realfast has been involved in a number of other localizations and discoveries. So we have one blind discovery that was obtained in a search of another field. You can see that it's associated with a dwarf galaxy. This was right at our sensitivity threshold, and we argued for a long time about its reality, but came away convinced that there's a high probability that it is a real FRB. A number of localizations, and two of which also include the discovery of persistent radio sources, along with the localization of the FRB. We've also discovered a number of rats in the data, and there's a pending paper on that subject. So commensal searching, this is a somewhat old graph, but showing just the accumulated amount of data early on when we turned on the commensal searching capability. But it's running now whenever someone is carrying out LSC or X-band continuum observations with 10 millisecond integrations. As I said, a big effort was to get this to operate with the Very Large Array Sky Survey, which is an over 5,000 hour, 3 epoch survey of the sky above minus 40 degrees declination. It's in S-band, so 2 to 4 gigahertz, and it's fairly sensitive. It's about 1 or 2 minutes per field, roughly. You can see some of the coverage. They're now going into the beginning, the third epoch, or the third epoch is underway. And realfast co-observed with the second epoch, and we are participating again in the third epoch. It's an interesting technical challenge to get searching work in the on-the-fly observing mode that VLAS uses. But really, this generates an all-sky FRB and pulsar search at S-band, which hasn't been done before. Okay, I think I have 2 slides, and I will be done. Thank you. And so, just as an example, here is detection of a known pulsar in VLAS that comes up in our automatic detection system. And so here's my summary slide. I think the road to getting to this system was long and complex, and it required a lot of innovation and experimentation in hardware, software, and algorithms. I think we didn't realize when we started this, but because we didn't know about the existence of repeaters, but realfast's greatest strength has clearly been as a follow-up tool for studying and localizing repeaters. Blind discovery has not been as successful as we anticipated. This is in part because we couldn't achieve ultimately the time resolution we wanted, but there's probably some assessment of rates and sensitivity that we need to address in a paper on the overall performance. I think there's a huge opportunity to do some interesting things with this commensal VLAS search. There's a really large volume.
Jeff, would it be okay for you just maybe, people can read the slide and I think it's very clear. If you want to leave it some time for people to ask questions, I'm hoping that we have an opportunity for that. Okay.
Yeah, sure, absolutely. Yeah, I'm done.
Okay, thank you. And thank you. Do you have questions from here? Tomo.
Very nice talk, Jeff. You said that there's a variability in 12.11.02. I'm wondering what's the time scale? Do they have like a millisecond time scale variability? What's the time scale? And also, did you observe during the active phase?
So we studied the variability of the persistent radio source. We certainly didn't see any short timescale variability. We wouldn't have been sensitive to that. It's quite faint. It's about 100 microjansky signal strength, and so requires a reasonable integration to see it. If I recall correctly, there was some slow evolution to the flux density, but months or that sort of time scale, and not anything rapid, as rapid as milliseconds or even days.
Did you observe during the active time frame?
Oh, yes. I think, as you know, the 12.11.02 seems to have these episodic moments, and the localization, the first localization occurred during one of these rather active periods, and so we didn't see any changes or variability in that time.
Okay, I'm going to ask CT to set up his talk, and meanwhile there's just one more online question we can take from Curtin, please. But CT, please to set up your presentation.
Yeah, thank you very much. Clancy here, Jacob from Curtin University. So as you know, we're now venturing into the realm of image searches on ASCAP with our backup system, and I understand Keith's been in touch about how to optimize. Two quick questions. One, I missed which search algorithm you actually ended up using. You showed these really interesting results on efficiency, and I missed what the solution was you ended up using.
Oh, sorry. So we ended up just using brute force imaging, and it turned out that we really didn't need to. We had sufficient computing power. The subtraction of the mean visibilities was quite useful because then all you have to do is search for any excess power in the dirty image. And then you know whether or not you have a candidate.
Yeah, okay, great. I'll keep you on the Slack if you want any more questions, since I think the organisers have already moved on.
Okay, thank you. We'll have to move on to the next talk by CT, but let's just thank Jeff once again.